Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level physics questions. So here's our first one. A small spherical mass, m equals 0.35 kilograms, is attached to one end of a light string. So I'm just going to draw this out myself. So the mass is 0.350 kilograms. And the other end is attached to a frictionless pivot that is itself attached to a ceiling. So that's the attachment point. It's released from rest at 40 degrees. And then at the instant that it passes through a 20-degree angle, so that's 20. Maybe I'll do that. Just to make it a bit more obvious. At that instant, the speed is 2.439 meters per second. Okay, and so now for A, it wants to calculate the magnitude of the radial acceleration at the instant it passes through the 20-degree angle. Okay, so the radial acceleration is just A, right? And now remember that F equals ma, which in a centripetal motion is mv squared over r, where v is our radial velocity. So then A is v squared over r, which is right. So A here is our radial acceleration, which is this value. So that's good. That's what we're supposed to be getting, and it's related to our tangential velocity, which is what's given in the question here. So A is v squared over r, which is 2.439 meters per second squared, over our r, which is given in the question as 1.75 meters. Now if we do this out on our calculator, we get 3.399 meters per second. Okay, so there's our radial acceleration. And now B is to calculate the tension in the string at the same instant. So if we do up our free body diagram, we've got our 20-degree angle. And so we've got mg, and then tension, and those are the forces that are acting. We can separate our mg into a radial and a tangential component. So our mg is straight down. Always mean to expand it. Okay, sorry. MG is straight down. So the radial component here and the tangential component here. And so we can see this is a similar triangle. So that angle there is 20 degrees. And so then this is mg cosine of 20 degrees. And this is mg sine of 20 degrees. Okay, and so then if we look in our radial direction, we have our forces are the tangential force. I'm scared of that little vector symbol because I'm just looking in the radial direction. Our tension, which acts straight up, minus mg cosine of 20 degrees. And that equals our MA. So that means that we can rearrange this for our tension. So our tension is just MA plus mg cosine of 20 degrees. And recalling too that our acceleration we calculated is radial acceleration, so it will be in the direction of the tension, so it should be positive. Just to double check some of our directions there. So then our tension is going to be 3.3, nope. Yeah, 0.350 kilograms times our 3.399 meters per second. That would be squared. Plus 0.350 kilograms, 9.8 meters per second squared, and times the cosine of 20 degrees. Now I seem to have missed this acceleration component here, my mistake. So I'm just going to add it in here now. So then our tension is 1.18965 newtons. Oops. Newtons plus 3.8 times 20 degrees cosine, 3.223146, which is equal to 4.413 newtons. So there's our tension. There's our tension there. Okay. And so then checking through the solution here, there is actually no solution given. So then this is all there is. Okay, so there's our question there then, and I'm just gonna just say incomplete then. All right.